I'm Keitaro Tanaka from Waseda University, Japan. In this extended video, I'd like to make a more detailed presentation about our paper, Manifold-aware deep clustering, maximizing angles between embedding vectors based on regular simplex. This work was done during an internship at Sony. This video is organized like this. You may jump to the content you'd like to watch. First of all, I explain deep clustering. Deep clustering, DC, is one of the very famous methods for monaural speech separation. DC estimates a binary speaker mask applied to the input spectrogram. For example, in the case of three speakers, given the input spectrogram shown on the left, DC aims to output the binary speaker mask shown on the right. Specifically, in DC, time frequency bins, TF bins, are grouped by speakers in an embedding space to get the mask. To achieve this grouping, DC estimates a high-dimensional embedding for each TF bin of an input spectrogram. This embedding is achieved such that two embeddings come to be close to or far from each other, depending on whether they belong to the same speaker or not. After this embedding, TF bins can be grouped by speakers using a clustering methods like k-means. We take a closer look at this embedding. For a while, we take a two speakers case as an example. The input of DC is a mixture spectrogram like this. For the input, DC assigns a d-dimensional normalized embedding to each TF bin using a DNN. After the assignment, DC considers the inner product distances between all embedding pairs. Actually, these distances show the cosine distances since each embedding is normalized. Next, DC controls these distances in a supervised way. During training, we know the true assignment of each TF bin based on the dominant speaker of the TF bin. Therefore, the supervision is conducted to make two embeddings of the same speaker close to each other, and make two embeddings of different speakers far from each other. As mentioned before, this matrix, which is the output of the DNN, shows the cosine distances between all embedding pairs because of normalization and inner product. For this matrix, DC defines the correct target distances with 1 and 0. 1 is defined for the pairs of the same speaker, and 0 is defined for the pairs of different speakers. Following the original paper, we represent each matrix as follows using V and Y. Then, DC's training is done with DC loss LDC. LDC is the square of the Frobenius norm between the two matrices. Actually, LDC is calculated with its expanded form for faster computation. What is important here is that the transpose of matrix Y shows one-hot vectors as the dominant speaker indicator as follows. So far, we have reviewed the details of DC. Here, one question arises which directly relates to our proposal. How would be the embedding space? Again, we remember that each embedding is normalized. Therefore, each TF bin is embedded on a hypersphere, and the distances are shown as the cosine distances. In the correct target, 1 means 0 degrees, and 0 means 19 degrees. According to this definition, we can see that DC limitedly uses a part of the embedding space as highlighted in this figure. Based on this consideration, we propose our method called manifold-aware deep clustering, MDC. Our method aims to maximize the target angle. In the case of two speakers, we expand from 0 degrees or 19 degrees to 0 degrees or 180 degrees. By doing this, MDC not only maximizes the angle between two embeddings belonging to different speakers, but also allows the use of previously untouched size of the hypersphere due to its overall symmetry. This theoretically enables us to train a DNN having a maximum spatial efficiency for each mixture. As we change the target angle in the embedding space, the matrix for the supervised training also changes. Since the cosine of 180 degrees is negative 1, the correct target matrix of MDC comes to be like this. 0 is replaced by negative 1. As mentioned before, we need the transpose of matrix Y or Y itself for faster computation. In two speakers MDC, the transpose of matrix Y is given below, though this is just an example and there exist many other representation forms. So far, we have taken a two speakers case. In the case of three speakers, we should expand from 0 degrees or 19 degrees to 0 degrees or 120 degrees like this. Such embedding can utilize the whole embedding space with its overall symmetry. Again, as we change the target angle in the embedding space, the matrix for the supervised training also changes. Since the cosine of 120 degrees is negative a half, the correct target matrix of MDC comes to be like this. 0 is replaced by negative a half. In three speakers MDC, an example of the transpose of matrix Y is given below. You may check the correctness of this representation by calculating the inner products manually. We have explained two and three speakers case. However, our MDC has been too ad hoc so far, because we needed to specify the target value of inner products and the transpose of matrix Y according to the number of speakers. Here, another concept comes into play to break through this situation: the notion of regular simplex. Our MDC can be generalized for an arbitrary number of speakers by considering the nature of regular simplex. A simplex is a generalization of the notion of a triangle or a tetrahedron to arbitrary dimensions. Especially, a regular simplex is a simplex of which all edges have the same length. A regular simplex is also a regular polytope at the same time, and thus it has the highest degree of symmetry. Several examples of regular simplexes are shown below. Actually, the positional relationship of each speaker in the embedding space of MDC is equivalent to that of the vertices of a regular simplex. You may see the cases of 2 and 3 speakers below. We can prove this equivalence generally. If you'd like to read it, please check our paper. The proof is in section 221, Introduction of Regular Simplex. Motivated by the above discussion, we consider embedding an n-1 dimensional regular simplex in a normalized hyperbole by considering endpoints, where each point represents a mixed speaker, as follows. This point is represented as a row vector corresponding to each speaker, and giving the generalized target value of the transpose of matrix Y in MDC. Deductively, the inner products are calculated as follows. For the same point, or the same vector and the same speaker in other words, the value of the inner product becomes 1. This ensures that each vertex is on a normalized hypersphere. For the different points, or different vectors, or different speakers, in other words, the value of the inner product becomes -1 over n-1. This gives the generalized target value of inner products in MDC. I said deductively because in the generalized MDC, the generalized target values of the transpose of matrix Y come first and the inner products are calculated next. Though in the ad hoc MDC, the inner products come first and the target values of the transpose of matrix Y are set depending on the inner products. MDC has another powerful characteristic, its high practicability. The difference between DC and MDC is just one term. In other words, the difference is in matrix Y or its transpose. Also, since the difference appears only in the loss function during training, MDC has no effect on the original DC's inference part. Therefore, MDC can be used in other existing DC-based methods, such as the chimeral network and the Kerberos network. The change from DC to MDC improves the accuracy of such methods as well. Now we see the results of our experiments. These are the results of quantitative comparisons between DC and MDC. As shown in this table, you may see our MDC outperformed the original DC in almost all cases. This is an example of the results of qualitative comparisons. This is the input sound.
The female produces a litter of 2 to 4 young in November and December.
Ashland is expected.
These are the results of the original deep crossing.
The female produces a litter of 2 to 4 young in November and December.
When its initial litter offering is completed, Ashland is expected.
Next, these are the results of our manifold-aware deep clustering.
The female produces a litter of 2 to 4 young in November and December.
When its initial public offering is completed, Ashland is expected.
You may hear the improvements. We added the spectrograms of the ground truth. Also, you may see the improvements at places that have been circled. These are the results of quantitative comparisons in the chimeral network between DC-based one and MDC-based one. As shown in these figures, you may see our MDC also improves existing DC-based methods. Finally, we note an important insight. That is, in the case of the infinite number of speakers, MDC is theoretically equal to the original DC. There, as you may see, each vector and the value of inner products come to have binary values. Conversely, we can say that DC always uses the positional relationship of each speaker of MDC with infinite speakers. Actually, since n is a finite number, MDC is theoretically superior to the original DC. The performance of MDC theoretically gets closer to that of DC as n gets larger, which matches the previous experimental results. In summary, we proposed manifold-aware deep clustering, which enhances hyperspace utilization more effectively than the original deep clustering. The difference between DC and MDC is just one term, and thus it is easy to implement and use. By considering the nature of regular simplex, MDC can be generalized for an arbitrary number of speakers. In the case of infinite speakers, MDC is theoretically equal to the original DC. Furthermore, MDC has high practicability for existing DC-based methods. If you are interested in further information, please check our paper or contact us. Thank you for watching. I'm looking forward to seeing you at the conference.